Good day everyone, my name is Pathun Prasanga. Today I am expected to present my instrumentation course project titled A Study on the Design, Modeling and Control of an Inductive Power Transfer System for a Parking Lot using multiple energy sources. This research was conducted under the supervision of Dr. Mohsin Jamil. I will take you through the motivation, design, simulation result and conclusion of this project, which aims to contribute to the future of EV transportation in a sustainable and smart way. The rapid growth in the electric vehicle adaptation globally is pushing the demand for safer, more efficient, and user friendly charging infrastructure. Traditional plug-in chargers, although widely used, come with several limitations. These include mechanical wear and tear, safety hazard in harsh environments, and overall convenience to users. Inductive Power Transfer or IPT addresses the issues by offering a contactless and wireless way to charging using magnetic field to transfer power. This technology enhances users' convenience, minimizes maintenance, and significantly improves safety. Furthermore, integrating IPT systems with renewable energy sources like solar and wind can make EV charging not only more efficient but also more environmentally sustainable. This project aims to demonstrate a clean and particular IPT based EV charging solution suitable for urban parking areas. The core objective of this project were multi-told. Firstly, we aim to develop an electric vehicle charging system powered by renewable energy sources, particularly solar and wind power. Secondly, we needed to create a control strategy for managing the flow of power and ensuring effective charging behavior. To analyze the feasibility and performance of the proposed system, we used two powerful simulation tools, HOMER Pro for system level energy modeling and MATLAB Simulink for the detailed design and simulation of the IPT circuits. These tools allowed us to assess both the technical and economic aspects of the system. The overall goal was to build a wireless, efficient, and eco-friendly charging system that could potentially be implemented in real-world parking lots. As cities around the world shift towards cleaner energy and electric mobility, the limitations of conventional EV charging methods are becoming more apparent. Plug-in systems require manual effort, suffer from cable degradations, and are prone to accidents, especially in wet or icy conditions. Inductive power transfer technology, which uses coil and magnetic resonance to wireless transmit energy, emerge as a safer and more convenient alternative. When coupled with renewable energy resources, it drastically reduces greenhouse gas emission and reliance on the conventional power grid. In this project, I focus on designing and simulating an IPT system integrated with solar and wind power, aiming to address not just energy demands but also the sustainability and reliability of EV charging infrastructure. The study was based on Parking Lot 18 at Memorial University, which served as a case study location. We estimated that 27 electric vehicles could be charged daily, with each requiring around 19.8 kilowatt hours per energy, resulting in a total daily load approximately 534 kilowatt hours. The proposed system includes multiple components: photovoltaic solar panels, wind turbines, a diesel backup generator for redundancy, and a battery storage unit to manage energy fluctuations and nighttime charging. The system was designed to operate with 6.6 kilowatt hour IPT chargers, which are commonly used for electric vehicles. The integration of renewable energy sources with wireless charging infrastructure is what makes this design both innovative and practical. The methodology followed a structured approach which first we selected the study site and conducted detailed load estimation based on the number of electric vehicles and their average energy consumption. Next, we use HOMER Pro to simulate the hybrid renewable energy system. Incorporation real-world solar and wind data from St. John's, Newfoundland. This helps us model the daily and seasonal variations in power generation. Following that, we design the IPT system in MATLAB Simulink, focusing on the resonance circuit parameters and coil design to ensure efficient energy transfer. Finally, we performed a comprehensive performance analysis evaluating the power output voltage, current behavior, system efficiency, and battery state of charge. The goal was to create a system that remains stable and efficient under variable energy conditions. Using HOMER Pro, we created a detailed model of the hybrid system. The simulation included Canadian solar PV panels, Bergy XL10 wind turbines, 10 ABB converters, and a diesel generator. Real wind speed and solar radiation data were used to ensure realistic performance. The system produced an annual energy output of 250,626 kilowatt hours, of which approximately 84% came from renewable sources. The model also showed that the system generated 29,386 kilowatt hours of excess energy annually, which can either be stored in batteries or used to provide additional loads. This level of renewable penetration not only reduces operation costs but also minimize carbon emissions aligning with global climate. In this page, you can see the cost of summary analysis and electrical result. From this one, we can see total net present cost is around $1.09 million, and the operating cost is $16,229, and the levelized cost of energy is $0.4336, and this we can see total replacement cost is $28,593, and the total O&M cost is $166,227, and we have to spend $45,000 to fuel. And we can see another the other slide. There is electrical result in the beginning, and we can see the excess electricity was 29,386, which is percentage 11.7, and the zero unmet load. And the other one, Canadian solar demand 60,000 kilowatt hours per year, and the wind turbine 149,776 kilowatt hours per year. Altogether, total gets 250,626 kilowatt hours per year, and the operation cost is $16,229. This slide we can see renewable penetration and carbon emission. First, we can say the total renewable production divided by load is 108%, and total renewable production divided by generation is 83.9%, and we can see nominal renewable capacity divided total nominal capacity 36%, and we can see the total net present cost $1.09 billion. And the other section we can see the carbon emission. Carbon dioxide emission gets 16,831 kilogram per year, and carbon monoxide gets 3,685 kilograms per year. This slide presents the detailed result from the HOMER Pro simulation, focusing on both financial and electrical performance. Starting with the economics, the system net present cost is approximately $1.09 million, which represents the total cost over the system's life including installation, operation, and maintenance. The levelized cost of energy, which is measure of the cost per unit of electricity generated, is about $0.43 per kilowatt hour, indicating reasonable affordability for a hybrid renewable energy system. The capital cost along was $882,677, but due to high penetration of the renewable sources, operation cost remained low. On the energy side, the system generated a total of 250,000 kilowatt hour annually. Of this, wind power contribute around 149,000 kilowatt hours and solar PV contribute 60,000 kilowatt hours per year. The excess energy of 29,386 kilowatt hours or 11.7% could potentially be stored for later use. Importantly, there was zero unmet load, meaning the system reliability met all EVs and auxiliary power demand. The system carbon emission were calculated at the 16,831 kg per year, far lower than fuel-based alternatives, highlights that project's environment benefits. Here you can see the MATLAB Simulink model of the system. In MATLAB Simulink, we model the inductive power transfer circuit. The system includes a high-frequency inverter, compensation networks, and coupling coils. The goal was achieve efficient wireless power transmission from the source to the vehicle battery. We considered parameters such as resonant frequency, multiple inductance, and coil alignment. By simulating these elements, we were able to predict system behavior under different operation conditions. The model provided insights into the dynamic response of the IPT system and helped us fine-tune the system designing of the better efficiency. The simulation showed that the output voltage increased smoothly to 400 volts within approximately 2 seconds, indicating fast system response. The EV charging current remaining steady in the range of 40 to 60 amperes, which is ideally for safe and efficient battery recharging. The primary coil current was around amperes while the secondary coil carried about 78 amperes. These results confirm effective energy transfer and minimal losses. The waveform responses were clean, indicating that the system is stable and well tuned. This part of the simulation analyzes the contribution from the solar and wind resources as well as the battery performance. The PV output range from the 15 to 25 kilowatt, and the wind turbine contribute between 12 to 18 kilowatt depending weather conditions. The battery operation between 16% to 18% state of charge, reflecting healthy charge and discharge cycles. No load was left unmet, and the system maintained stable operation throughout the day. These results underscore the reliability of the hybrid system in real-world scenario. And this is our future works we can observe. There are several directions of the future research. On one area is dynamic charging, where IPT systems could charge EVs while they are moving slowly, such as in drive-through or bus lanes. Another area is vehicle-to-grid integration, allowing bidirectional energy flow to help with the grid stability. Developing smart charging algorithms using artificial intelligence can improve energy distribution and user experience. IoT-based monitoring could enable real-time diagnosis and predictive maintenance. Finally, real-world pilot testing and the use of advanced MPPT algorithms would further validate and enhance the system's performance. In conclusion, this project has demonstrated the feasibility and benefits of wireless electric vehicle charging system powered primarily by renewable energy sources. By integrating solar and wind power, this battery storage, the system not only ensures reliable energy availability but also significantly reduces dependence on fossil fuels. The annual energy production of over 250,000 kilowatt hours was significant to meet all projected EV and auxiliary demands, with zero unmet load reported, highlighting the reliability and self-sufficiency of the system. Economically, the system maintained an competitive levelized cost of energy of $0.43 kilowatt per hour and net present cost of 1.09 million, which proves its cost effectiveness over the system's lifetime. From a technical standpoint, the MATLAB Simulink model verified that the IPT system achieved high efficiency up to 97 to 98% with stable charging current and a smooth output voltage profile. These results confirm that the IPT can effectively combine with renewable energy in urban parking lots of offer a scalable, clean and user-friendly solution for EV charging. Moreover, this system supports to transition toward greener sites cities by cutting down on emissions and promoting sustainable infrastructure development. It serves as a strong foundation for future innovations like dynamic charging, smart energy management and IoT-based control in EV charging networks. To enhance the system's performance and practicality, it is recommended to increase battery storage capacity to better handle energy fluctuations and ensure uninterrupted charging during cloud or night time period. Incorporating more cost-effective and modular renewable components can help reduce installation cost. Maintaining a grid backup connection is also advisable for emergency scenarios. Lastly, user training and awareness on proper vehicle alignment and safe usage of wireless charging system will improve efficiency and adaptation in real-world parking environment. Public education and user training as wireless EV charging become more widespread. User many benefit from improved efficiency and user experience via education on safe parking alignment and use the best practical. Grid backup redundancy from energy power dependability in the event infrequent system failure. It is advised to retain a modest grid backup line even when the system displays zero unmet load. Thank you all for your time and attention. I would like to express my gratitude to my supervisor Dr. Mohsin Jamil and the Faculty of Applied Science and Engineering for their support. Thank you.